club. You're not here because you have to be, well, maybe some of you, but most of you, are here on your own volition, and, you're engaged, and I just love that. And whenever anybody mentions the Natural History Society of Maryland, I always put a plug in that I'm so impressed at what you're able to do on a shoestring, basically. I'm really impressed. So I did bring some extra volumes, some extra copies of volume 2, Smithsonian Press. I do not have any volume 1s left, and they won't print anymore, which is sad because there's demand for volume 2. This one includes the reviews of the turtles and dolphins from along Calvert Cliffs. So they're on the table over there, and they're complimentary. They're Smithsonian publications, so I can't sell them, and so they're there for the taking. So this evening, excuse me, this is the first talk that I've ever given solely on coprolites. So you guys are kind of like guinea pigs, and really, and I I've included, various coprolite stories in many of my talks, but this one is solely dedicated to coprolites. And so well, it's not really even finished because this is an ongoing thing, but this is like what happened this morning. And I should have put like where I was from. I didn't even put in like Calvert Marine Museum, but anyhow. So it's going to be a series of little vignettes, little stories about amazing coprolites that have come to me, and I just had to tell their stories. Now, I will also preface this talk by saying that when I was a graduate student at McGill University in Montreal, I went to a paleo conference at the University of Kansas in Lawrence, and there was a master's student who was giving a presentation on coprolites. And I thought to myself, man, why are you wasting your time on coprolites? Like, get a life. I felt sorry for him because I thought, whoever is going to employ a copropaleontologist or and so be careful what you criticize or what you deride. So here I am, and these fossils, like I said, have come to me, and I could not help but tell their stories. They were just too fascinating, too amazing, too unexpected and unusual. So this is a crocodile coprolite, and they're one of the more common types of coprolites that we find along Calvert Cliffs. And believe it or not, somebody has worked out the math so that if you know the diameter of the coprolite, you can calculate the length of the animal that produced it. It's a very simple mathematical formula, one that even I can contend with. And yeah, so I didn't bother putting it up here, but I just thought I would say that in passing. So, Calvert Cliffs is the only place in the world where feather impressions have been found in coprolites. There are 4 specimens known. We have 2 in our collection, and there are 2 at the Smithsonian. This is the Smithsonian specimen. You can see there's the feather impression. So we went from the bird. Okay, so yeah, don't get ahead of me. It's not as though the feather was on the ground. The crocodile came walking along, took a dump, and it landed right on the feather, picked it up like it was something, white plasticine. No, this was embedded in it, and I'll show that to you in the following. Here's a close-up view of it. This one actually is extra special because it's not just an impression. It actually has some of the original keratin that comprise the feather preserved in there, and that's a project that somebody who is into fossilized biomolecules should look at, because there's a research paper in there. Here's a second specimen, and this one is exceptional as well. And here's the whole copper. Well, here's most of that copper. And I've circled. Oh, I have a point now. I've circled the feather here, but when you look at the rest of this in sections, the broken pieces, you can see feathers are swirled completely throughout. So again, it's not just picked up. It was actually brought ingested a bird. So as you know, they do. They'll eat whatever they can get hold of, and they apparently have a low pH in their digestive system. So the bone is digested, but acid doesn't work very well on keratin. So that's why it can be resistant, and it can pass all the way through and be preserved in those coprolites. The resolution is just as bad. I took a little tiny piece of this, took it to the Smithsonian, and they SEM, that scanning electron micrograph. And here you can see so I'm just going to go over this illustration here. So you have typical that, right? You have the radius, which is the trunk of the tree. And then you have the branches coming off, right, which are referred to as barbs. And then off of those, you have smaller little branches referred to as barbules. And those have the Velcro-like mechanism that holds the vein of the feather together. So what you're looking at here are adjacent impressions of barbs. And here are the spaces between which, the fecal material filtered in between the barbules. So the barbules would have been in these open spaces. They're not these little filaments here. That's the fossilized species. And so that's astounding at the resolution. Here's the scale, 100 microns. There's 1 million microns in a meter, right? So you've got just over, a millimeter in view here in this photograph. Here is, up until recently, this was the most amazing fossil that had ever come into my office. It was collected by Dougie Douglas, and he found it along Calvert, and I'll show that to you in just a minute. And as soon as I saw it, I was like, I will not live long enough to see another fossil like this. So here you have a crocodile coprolite, in which are so this is where Dougie found it. This is Dougie Douglas. And this is just the north end of the western shore, and it's really long solid class. So it's a Miocene age coprolite. And yeah, so it's a sharp bitten coprolite. So because it's a natural mold, it's an impression, I put a perimeter of plasticine around here, and then I mixed up a silicon rubber casting compound, poured it in there. 24 hours later, I peeled it out, and that's what we're looking at down here. The natural mold, right? The cast made from the natural mold of the shape of teeth. And so this little tooth right here, that's the midline, that's right there. So it's the synthesis of the two halves of the jaw coming together. You can't tell from the shape of these teeth if they're upper or lowers, but you can tell that these are teeth on one side of the synthesis, one side of the jaw, and the other teeth on the other. And because of the shape, well, we know that they're from an extinct tiger shark. And we know from studying modern tiger sharks that they will bite things to assess their palatability, right? Is this something I want to eat? And tiger sharks are notorious for having all kinds of things in their stomachs that they ought not have there. So it doesn't always work, I guess, that they're rejecting things. I mean, I've even heard like license plate. I don't know if that's true or not, but they will eat all manner of things. So it's clear from this that the tiger shark did what? Did not eat the fecal mass. It just did it, right? Yeah, decided, okay, I'm just not that hungry. So how did those bite marks come to be preserved in the feces? So it could have been that the marine croc took a dump in the water and they were just kind of floating around, and the shark came up and did it, and again, compressed the feces and then let it go. They sank to the bottom, were entombed by sediments, and 15 million years later, they eroded from Calvert cliffs and found it and brought it to my office. Sorry. Or I enjoy this like ongoing commentary. We're already made it.
No,
How big was the tiger shark?
Oh, super good. I've never tried to calculate, but that could be done. Because I've learned since this little paper that there's a strong correlation between the width of the jaw of a shark and its total body length. So I have not done the math for this, and I'm assuming that it could be calculated because you know the width of the teeth, and so you can calculate the width of the jaw. So that could be done. So there's a little project for you.
So you just got homework.
I like turtles.
Yes, Adrian.
How shallow a depth of water is that shark gonna go? Or how deep is that crop?
It's a marine rock. I do not know how far out into the marine sea it could have gone. So we find crocodile bone throughout the Calvert Cliff section. It includes open marine conditions, right? So I don't know how many miles that would represent. Yes.
I was doing isotope work on the crocodiles. Wasn't his main finding that they were like in pretty open marine environments? I feel like
It wouldn't surprise me.
I think that's what you found was.
Since we find crop throughout, the Calvert Cliff section, which includes near shore, right, like the Raritan Bay, just south of Long Island, right, which is kind of a protected bay. That would be like the St. Mary's Formation, up to fully full salinity conditions, open marine environments. So that, I don't think that would help us, in this story. Okay. When you flip the coprolite over, you'll notice that there are two impressions, but they're not as deeply impressed, right, into the fecal mass. And, in the middle of the night, I'm thinking about this, I wondered, well, why is that? You would think if the shark was just kind of nosing around in the sediment or it was floating and it fitted, that the upper and lower teeth would penetrate equally, but they didn't seemingly do that. And so, this idea came to me that maybe the fecal mass, the feces, were still in the abdominal cavity of the marine rock when the tiger shark plowed into it, or when it was disemboweling it and it was biting them. And so maybe that would explain why there's that differential penetration of the teeth. I can't prove this, but it makes a great story.
Well, it certainly would make sense that it would come up from underneath the faster.
Soft, yeah, and there are the scoots, right, that are the protective body armor.
Correct, so
That's a
it is
characteristic.
a role for that.
Yeah.
Anyway. Such a lot of
Surgical, yeah.
Surgical treatment, wow.
You're all over your Marvel comic superheroes. Where am I going with this? I'm showing this because this guy does something amazing with his eyes. Okay, and the next creature I'm going to show you does something amazing with his eyes. It's this animal, the electric stargazer. They're local. They live maybe down the mountain of Chesapeake Bay in the Atlantic. And these are ambush predators. This one, the photograph shows it kind of sitting on the ocean floor. Typically, they would bury themselves until just their eyeballs are shown. Okay, and you'll also notice that their mouth is not terminal here where you would expect a fish mouth to be. It kind of looks like this muppet. That's the lower jaw, kind of like a muppet. And so it opens up. And so when their suitable prey comes in, we just kind of open their mouth, expand their laryngeal cavity, right, and clear the gills, and they suck in their prey. But they have another little trick, which is super amazing. And that would be the electric part. That their muscles behind their eyes are said to be electrogenic, which means that they can generate and store like a capacitor an electric charge, just like an electric field. And somehow, and I don't know how they do this, they're able to discharge and stun their prey. Okay. So here is the type specimen of a Miocene electric stargazer that was found by one of my first assistants, Phil Conant, a super gifted natural fossil finder. And this is the part of the skull that's referred to as the neural cranium. That part of the skull that houses the brain underneath here. This is the top of the skull. You're looking at the dorsal surface, and this is the texture, which is characteristic of the bones, the dermal bones of this kind of fish. This is the underside. This is like the brain, the palate kind of the mouth, and then just the back and the side view. So here are where the eyes would be, but the eyes don't occupy all of that opening. The bony openings are larger to accommodate those electrode muscles. So here are some photographs. This is the type specimen. A modern one here has slightly larger openings. And then this is a mummified specimen. And again, you can see the eyes here. And then this is a cleared and stained one where you can see the bone, but the soft tissue has been left. And so you can see that there are the eyes. And then here are these special electric generating muscles. This is a parasitic. So when we describe this animal, this is another specimen that was found by Gene Rupert. And what's amazing is you're looking at the top of the skull, but when you flip it over, and some of the bone here on the ventral side, underside of the braincase broke away, you go like, hey, wait a minute, what is all that stuff? The brain is filled with these little like pellets. And initially, I was like, are those eggs? That it kind of look like little flying eggs. Like, no, this is a marine environment. There's no like insects that's gonna lay their eggs unless this fish was washed ashore, had eggs laid in the braincase and then got like washed back out to sea. I just, that, didn't. It turns out that those are micro-coprolites. So you can name, in paleontology, you can name trace fossils. So a trace fossil is anything that represents the activity of a once living animal. So trace fossils include like footprints, nests, eggs, fecal feces, scratch marks, burrows, those sorts of things are trace fossils because they're not part of a living animal, but they're evidence of the behavior of those animals. And so these little micro-coprolites, here is the scientific name, Coprolite oblongus. So what animal got inside this fish's brain, ate the brains, and replaced it with feces? So it would have to be like a squishy, tiny, flexible. I like to say this. This animal has actually worked. It's probably a marine worm, a soft-bodied animal, because they're getting into really tight space, right there confined. And what's amazing is that, yeah, they're just like, here's insult to injury. You're dead. I'm gonna crawl inside your brain. I'm gonna eat your brain, and I'm gonna fill the whole space with my feces. Here's one of those under a scanning electron microscope. So that's about 1 millimeter long. About 30 slides you take it off. What's amazing about these marine worms is that they weren't just scavenging fish, they were scavenging whatever was out there. And because we found them inside, now all of these are actually part of the clamshells. It's the sediment that's infilled the clamshell. And this is what they look like, all these little people pellets. Once you start seeing these, they show up in a multitude of places. Here's a bunch that are infilling these Miocene barnacles. Like you can see them in here, you can zoom in on one of these, and there they are. These animals, they die, and the worms are kind of, the worms crawl in, the worms crawl out, they eat your guts like sauerkraut. That's exactly what's happening. Here's one inside a moon snail over here. You can see the coils of the moon snail really are there. And then here is one that was just seemingly moving through like an earthworm through the sediment, like a detrital feeder, feeding on whatever was there and putting out little poops behind it as it moved along. Here is a crab claw, stone crab, and all the inside, when that outer layer was broken away, you can see it's completely infilled.
I would say, how much they pack into one small space, like, I wouldn't want to hang out by pieces as well. And they just. Trade in this. Packet.
Right, why they would seemingly go to the bother of like, hey, I've got nothing else to do with my life. I'm going to spend day after day carefully filling these kind of like tetras, making sure I can pack as much into this space as possible.
Yeah. Another question. Okay, so since like we can correlate the diameter and length, I guess, well, mostly the diameter of the coprolite to the species, we think that maybe that would work faucet for analytes. And if that's true, then we have different representatives inside that some space, like maybe multiple
Size.
individuals represented by multiple size.
So they do vary slightly in size.
Species.
Well, I mean, yeah,
Like
if you
colony?
took a micrometer and measured them, they would. So I don't know how many individuals work together collaboratively, to produce this. That I don't know. I don't know enough about marine analytic biology to have an answer to a question like that. But if you are so disposed, like if anything comes up and anyone wants to do a little research, you can run with it. So here is end of story. Here's another story. This is a couple that goes down by Mike Gilbert, who's one of our long-time volunteers, lives in scientists, so has access to prime real estate along Calvert collecting fossils. Here's a big crocodile coprolite, and you'll notice that there is this like circular opening in it, and it just conveniently broke here. And when you open them up, this is what it looks like. And so you can see that there was some organism that actually tunneled into the big crocodile coprolite. So this was probably the fate of most of the feces along Calvert Cliffs, right? They did not all preserve. Because if feces were not recycled, life would have ended on planet Earth because all biologically active molecules would be locked up in feces. So thank goodness that stuff is, it's recycled. There are animals that engage in coprophagy, they eat feces, bacteria that decompose it. But this one here was not completely consumed, but it did tunnel into it. Here are the three other sections of the coprolites that have had animals tunneling into it. And you can see the little sort of bite marks from the mouth parts. Again, it's probably some sort of worm, but it's a much larger diameter. So again, we don't know. This is a fun project I did with a colleague, super brilliant colleague in Italy, Alberto, Colorado. Colorado. This is so much fun to work with. Anyways, this is a scientific name we came up. So we named this. We named this trace fossil Trans excrementum cuniculus. Trans meaning like through. Excrementum referring to the feces. So, and cuniculus means tunnel. So this is the tunnel that goes through the feces. How brilliant you have to be with the trace fossils. I'm paid to do this stuff. It doesn't get any better. Here's another story. Billy Palmer, the late Billy Palmer. Again, a natural fossil finder. Oh, did I mention I'm no good at finding fossils, but I've surrounded myself like you with people who are naturally gifted at finding fossils. And so Billy brought this to me. He gave it and donated it to the museum. He collected this in his coprolite in King Street in South Carolina. And yeah, so kind of a fun story because you can see that there are two orders of magnitude of white, like raking marks over the surface. There are the bold ones, and then the white arrows are pointing at these really fine ones. So try to figure out what kind of animal, freshwater, this is a freshwater deposit, what kind of animal did this? Well, they're parallel, and they're two orders of magnitude of teeth. And the only animal that I could match it was garpite. Gar, you notice they have these large median teeth, and then they have these lateral, fine lateral, and it matches perfectly. We took some plasticine and raked gar jaws in order to see to replicate it, and yes, in fact, we did. So we're quite confident that it was a gar. Now, gar sit motionless in water essentially, and they move very little. And again, they are ambush pretty well. They're opportunistically sort of ambush predators. They remain still until prey items come close, and then they very quickly will snap their head and jaws shut extremely rapidly. And so that's probably how it happened, that this, the feces kind of floating through, it went by, caught the fish's attention, and it snapped at it. Again, it was just kind of a grazing blow, both upper and lower jaws, you can see here. It grazed past it, and it just let it go. Here's another one. Excuse me, found by Buck Ward in Virginia. And again, it's a gar-bitten coprolite because it has exactly the same pattern where you can see the bold first order, and then you can see the very fine second order magnitude fine striations that were left by the fine teeth. And this is another fun project because we got to name this one Macicnus dimorphicon, di meaning two, more in reference to the two morphologies of the teeth that raise the surface. For years and years, we've watched SpongeBob in our house. The more recent ones, I'm not so crazy. But this is Barnacle. You noticed? No, I'm sure I missed it. So it's okay. You haven't missed out on much. The first two seasons are really good. After that, just went down. We have barnacles. Barnacles are crustaceans. They have a little arm, as you know, and they're filter feeders. They capture their prey. And they will also implant on turtle shells and on the bodies of whales. But here is the only known coprolite that I've ever seen that has what I think are the little bases, right, of embryonic, but juvenile barnacles that attach to it. Now barnacles, they have a big swimming larval stage, and at some point they have to settle down onto a firm substrate, which they anchor to. And then they start to grow. And you'll notice that all of these are approximately the same size. Not very big, maybe what, a quarter inch, 1/8 to a quarter of an inch in diameter, and nothing larger. So I don't know why they didn't continue. And I'm not even sure that these were made by barnacles. It's the best guess that I have. If anyone has any other suggestions, I would welcome them. And trace fossils like this made by the base of barnacles anchoring to biogenic material or even stone has been given this unpronounceable name, paleontology. This is the only slide we see in this session. It would fit the palm of your hand. Kind of has the right one, you know, where the crocodile took the boot and the way it closed, and you can see the kind of little pinch. I mean, you all do it. Okay, I know. It just happens. This is another Billy Palmer find from the same creek, King's Parade in South Carolina. And it's a partial turtle carapace, impression thereof, preserved in pieces. So this photograph was given to me by Billy, and I'm sorry that it's not clear, but this is the location where he collected along the Black River. And I've got a couple more slides just showing, you know, so they dig into the sediment, right? That's completely filled with all kinds of fossils. And it's a mixed biome of animals from the late Cretaceous to the Pleistocene. You can see sharks, there's turtles, crocodiles, mosasaurs, dinosaurs, equids, elephants, cetaceans, and coprolites. And the coprolites are the most abundant element of the fossil biome that's found. Here's another just showing the stream water. And most of those are probably coprolites. There's literally thousands of them that have been collected in the site. So you notice that the fossil itself is really dark like this. And there's this super nifty little technique that's been around since about 1930s. And I don't know how they discovered this, but if you take ammonium chloride, which is like a solid, it's a solid, and you put it into a Pyrex little test tube that's open on both ends, like a little ball, and then you heat it up over a Bunsen burner, it goes from a solid to a gas, it sublimates. And then you put a little bit of compressed air through one end, and it blows this white smoke out the other. And it's referred to as dusting or whitening a fossil. And it's super amazing technique. If it's not permanent, the fossil has to be sufficiently insulated or resistant that you can hold it under running water. Because you don't want to leave the ammonium chloride on it because it can combine with water and form hydrochloric acid and degrade your fossil. But at any rate, for the 10 minutes that you coat it, you can take amazing photographs. And I photographed the fossil under fluorescent light, and you look at that. So the detail is like that. So here are 3 views of the same coprolite, looking kind of down on the top. It's like a curved surface. Here you can see this curving surface, right? And then it kind of looks like the hull of the boat. And here's like keel. And here's looking at the ventral side, the underside, the keel. You can see it's very narrow and elongated. But in here is all the detail of the impression of this turtle shell. And there's so much information in here. When I started working on this project, I had no idea how much detail there is. And I'm just going to show you. So people that study turtles, they know all about the outer surface, right? They have this like little, very wafer thin little keratin that covers it and gives it the pattern in the turtle. But if the turtle dies and that comes off, then you see the bones underneath, right? Now in this fossil, both are actually visible. Both the outer impression and contour shape of the keratinous sheath that covered the baby turtle, and also the bony pattern underneath. So here's the outer scutes, keratinous scutes, and here's the bony pattern, and the two of them together. And there's the scale, and also we don't have all of the turtles, but because we have the midline, we can mirror image, so we get more of it preserved. And it matches most closely this Cretaceous and Paleogene turtle called Calvert. And so here's the size of the one in that coprolite as compared to a subadult and then a fully mature individual. So this turtle is known from the Cretaceous, right at the end of the age of dinosaurs, and then the major boundary, the KPG boundary, and then the Paleogene, which is the beginning of the age of mammals. Also, there are two groups of turtles. Pleurodires, pleural means side, right? The side neck turtles. They can't pull their head back this way, they have to wrap it around that. And then the cryptodires, crypto means hidden, the dire in the neck, so the ones that pull it straight back. Well, this kind of, this turtle here is actually a pleurodire. This is something that I didn't know when I submitted the manuscript for publication. One of the reviewers was a German neontologist, an expert in turtles. And when I got the review back, he said, you guys haven't even seen one of the most important things here. And that is that, and I didn't know this, that embryonic turtles or turtles in the egg have a different texture. As soon as they hatch out of the egg, the texture on their shell changes. And so you can tell, this is just a tortoise, this is a modern one. So this little pustule, little textured surface here, that's the embryonic shell. And when it hatches, it has this smooth texture. So you can tell, relatively speaking, the age of the individual. You know, was it embryonic or was it a young hatchling or older? So in the fossil, you can see here that we have the embryonic texture, the little pustules, and then we have the smooth texture here, which represents the hatchling shell. It's just amazing that that would be preserved. The arrows show the direction in which the feces came out of the body of whatever, I'll get to whatever animal. We don't know what kind of animal produced this fecal matter. But what I love is that this little keel shape down here, what was narrow and elongate, shows the shape of the cloaca, the opening that the poop chute that the feces came out of, right? And then it hit the turtle shell. And struggle. That's a very good way of thinking. It's just kind of like, I'm never going to eat the turtle again. Who knew that you could tell? You would know that from a coprolite. So here are the potential predators. If it's a Cretaceous, I mean, we don't know since it's a mixed fauna. There's been rework. If it's Cretaceous, there's dinosaurs, crocodilians, mosasaurs. Then if it's there could have been birds as well, but we'll include birds in the dinosaurs. And if it's Paleocene, then it's crocodilians or birds. So it could have been anyone of those.
You couldn't tell by the size of the port, you know, really pinched off. That's how it was.
So again, I have not spent a super lot of time trying to figure that out. And plus it's a soft tissue. So in a fossil form, you wouldn't necessarily know the length of the cloaca, right, in an extinct dinosaur. Now, obviously, if it's the Appalachiosaurus, it's presumably a larger, well, it is larger, Tyrannosaurid. The coprolite is like would fit pretty nicely in the palm of your hand. So it's not a big. But again, I don't have an answer to that question.
There's a question on Zoom, Stephen. If the turtle was embryonic inside an egg, how did the excrement touch the shell to make an impression?
Okay, so the turtle hatched out of the egg, and it lived for a while. And again, I don't know how long it lived based on the width of this. I don't know how much time that represents right there of post hatching. So it was not eaten while it was in the egg. Is that basically, am I understanding correctly?
I think so, yeah.
Yeah, so the baby hatched, it was kind of moving around doing its thing, and then it was eaten. And this might represent days or weeks, but probably, I mean, it's not that much time. Yes,
So that's why that shell's showing embryonic and hatchling.
yes, that's correct.
So it's in a transition stage, but then it would just all be hatchling or
That's correct.
mature at some point.
Well, it's.
When it's showing both, it had just been hatched in some,
That's correct. But
recent
the
form.
embryonic technically stays there, as the shell gets bigger, right? Each one of those scoops, right, that's what you're looking at here primarily are the keratinus, right? The keratin that covered the bony part of the shell. You're looking at an impression that
right,
was made in the feces of the outer surface of the shell. And so you're looking at this texture here is the embryonic texture of the little scoops on the outside of the shell while it's in the egg. And when it hatches out, it develops this new texture here, this smooth. But this, as the turtle grows, right, the scoops grow peripheral and they enlarge. But that the little center of it is it's not eroded at all. It's maybe sloughed off. As long as that's there, you can see the embryonic texture. So Kim Shire, for our press release, when its data came out, it was so strange. We don't know, it was mosasaur, dinosaur, bird, or crocodile. And there's our little Atlas turtle that got this is a more recent project. This is a crustacean preserved in a coprolite came from the Monkey River in Virginia. And it was found by Jason Osborne, who is a diver. He now lives in Texas, but there's a number of blackwater divers that dive in the rivers in Virginia and further south and find amazing things. But this is an isopod. So here you can see there's the full coprolite, and this was whitened with the sublimed ammonium fluoride, so that's why there's so much detail. And here you can clearly see the impression of the animal. This is the head end, and then this is sort of the tail end here with a little kind of appendage bar. And so it's an isopod, and they're pill bugs. And when you think of pill bugs, you think, well, how do I say it? Cute little animals. So I want to just point it before I get too carried away with the pill bug. Because of the impression, none of the cuticle is preserved, but it's a beautiful impression. And so I wanted to make a mold of it so I could see what it actually looked like, because it's hard to conceive, right, conceptualize what an impression is. If you want to see the negative, it's difficult to interpret, but the positive is so much better. So I sort of playing with a variety of, casting compounds, and none would work. Well, they would work, but I couldn't get them like deep into the little crevices here in those deep air pockets. And so what I had to do is go back to a technique that I used when I was a graduate student. There were some fossils from Nova Scotia of early tetrapods that were the bones were just impressions inside tree stumps, sigillary from Joggins, very famous fossil locality, which is now a World Heritage Site. And what you do is you take latex, rubber latex. It's like a coal cream, that consistency, or like mayonnaise, and you dilute it with water until it's the consistency of milk. And you put it in airbrush, and then you just basically like spray it on. So that way you get no air bubble. But you do get a very, very thin layer. So you put on like 8 or 10 of these very thin layers, and then you come in with a thicker latex. And then once it's cured, you can peel it out. So here's the peel, here's the polish. And so we're looking at that here. And then you can see all the segments back here of this tiny isopod. Now I said that, when you think of an isopod, you flip over a log and you see these cute little animals and you touch them and they look like little trilobites and they curl up and they're harmless. This isopod here, the impression, it's a marine isopod. They are nasty, nasty animals. They're parasites. And guess where they like to anchor themselves? Inside the mouth of their host. Here is this nasty little isopod inside the mouth of the clownfish. I have an isopod in my mouth. They hook onto their tongue, and they will actually eat the tongue of their host. Isn't that nice?
That's what happened.
Yes.
There's a question asking if the coprolite with the pill bug is from Blackwater, Maryland, or Black River, North Carolina.
Neither.
Trick question.
It's Pamunkey. It's from the Pamunkey River. Yeah,
In Virginia, you said.
Yeah.
I think.
yes, it is, it's lower Calvert.
It's black water.
So there are blackwater diets, but not a location, yes.
Thank you.
There were some other, like, if you wanna get grossed out, Google these parasitic marine isopods. Yeah, nasty,
Now-
nasty.
Now, the one in the coprolite, was that internal or external or?
Oh, good question, yeah, so what we think happened is that, and we don't know what animal produced the coprolite, that impression was preserved. It's a turtle, croc, or a marine mammal. I just got the review back today, and we had suggested turtle or croc, and one of the viewers said, well, how do you know it's not a marine mammal? And I like, okay, so I'm gonna have to be, I guess, a little more circumspect in that publication, but so we think that the predator ate the fish, dissolved the bone, but the cuticle survived because it's less susceptible to degradation than acid content of the GI tract. This is a fun little story. This coprolite was donated to us recently by Mark Bennett, who is a commercial dealer in fossils. And this comes from Nebraska, from the former Arner Ranch, now the Gulata Ranch. And this is the fossil here. This is the actual ungule. It's the distal little toe bone, a little tiny horse, Eocene or Oligocene horse, that was eaten by a dog, a bone cracking or bone crushing dog. And it passed the ungule, right, the last little digit, through without digesting or without even, like, the acid didn't even touch this thing. It's pristine. And what's super amazing is that you can see here in an impression of the actual sheath, right? The little nail, the little hook that covered that bone also passed through. And only after the feces had been defecated did that hook then decompose. But only after then the feces were firm enough to preserve the shape of the hook that covered it. Here are some photographs provided by Nevada of the former Arnold Ranch, now the ranch. They bought half of it. They bought the fossil half. And you can go and collect. You pay them a certain amount per day and collect. I would love to go there. It's just spectacular. It reminds me so much of the Badlands. I used to live in Alberta. It reminds me of that social park, but just super beautiful. And coprolites occur throughout here. So they don't exactly know the age of this because Mark Bennett bought it from an estate sale. And he doesn't know exactly where on the former ranch, what formation it came from. But he did donate it to us. So here's again another view of it with my hand so you can see how it's about, again, nicely at the palm of the hand. And so you can see that ungule, that little elastic, about the size of the end of your finger. Yes. So when you think about modern bone cracking or bone crushing animals, spotted hyena is the very best. They are the best adaptation at cracking and crushing bone. And if they're feeding on an animal, and it's not during the calving season, when wildebeests, there's lots of babies around, because if there are, they will just kill and eat a little bit of that. But if there's not as much prey around, spotted hyenas will eat everything. They will not leave anything for anyone else. They'll eat all the bone. And I thought that they were eating the bone because they wanted the bone minerals. And maybe there's some of that, but they're primarily interested at the food that's inside the bone, the marrow. And lesser carnivores don't have jaws and teeth that are as well adapted to crushing bone. And so they can't get that food resource that these guys have figured out. So here's the skull of the spotted hyena. And you can see how massive their teeth are. They're just like kind of these great swollen teeth, and the bone here is super thick. So their skulls are just like amazingly well adapted for crushing bone. It just so happens that the pH of the acid in their intestines is also very low, so highly acidic, and they typically digest everything. When they defecate, there's no little chunks of bone that come out. Now, there are lesser hyenas, striped hyena, and there's one other one, brown hyena, where chunks of bone will be found. Now, in the fossil record, yes.
Oh, sorry, I was going to ask you.
Okay, in the fossil record, here in North America, there were animals that were not as efficient as spotted hyenas, but more like striped hyenas, where they were bone cracking or bone crushing, but they would not fully digest all the bone that they had ingested. They would pass, they would void bone. And so here's this wonderful Asian jaws. Again, you can see how massive the jaws are. Look at the size of these primates, just huge crushing teeth to crack bones open. So borophagians were actually here during the Miocene as well. We found some, and we include them in the book, what will be volume 3 in the land mammal chapter. And so here's the little horse, Hyracotherium, which is this ancient horse compared to the size of a cat. And you can see that in the front hand, they had four digits, one of which was enlarged. And so this then became the book, right, in modern horses. And in the back, they had 3. And so what is preserved is this little bone right here. And I think this is the last coprolite. This was also donated by Mark Bennett. This was collected off Calvert Cliffs, not far from Madawaska by a diver. And Mark Bennett bought it from the diver, and he donated it to us. So Mark has been super generous with us. This is the most vertebrate bitten coprolite known anywhere in the world. You know, when I got that shark one that had the shark tooth impressions, I thought I'll never see anything like it. Just in here, like, that's a kind of a rival to that one. Because you can see here, look at these like tooth impressions here. And it's this like really narrow and elongate dental like tooth. What animals do that? And look at these like scoring marks over here, where kind of a series of teeth that were like in a line, fairly close to each other, kind of rake the surface. And when you flip it over, there are more bite marks here. In fact, this set right here and this set here represent upper and lower teeth of the same animal. And so I'm hoping that, again, I'll be able to figure out what kind of animal this is by making a silicon rubber cast of it. I think it was a dolphin.
Yep.
That was, and so like, I'm putting it because I think this idea came to that these guys are like, yeah. So we know that modern dolphins, right, they play with stuff. They're pretty smart animals, right? And they don't have video games and things and tools. Well, actually, but they will play with the puck fish and kind of like pass it around and they'll get caught. And so who knows? You know, it was a slow day in the Miocene marine ocean, and there was this like crocodile coprolite that they were kind of passing around and like kind of nibbling on. Who knows? But yeah. So yeah, this is year 26 for me at the Marine Museum. I love going to work. I have such an amazing job. I get to collaborate with so many amateur paleontologists and interns, and like Cedar is one of our interns, and volunteers. And Corey is one of our volunteers, and is also, you know, really instrumental. Like he found the other half of the lower jaws of the whale skull. So when I was in graduate school, I had no idea that so many people collaborate between these avocational paleontological communities and you know, professionals. So I'm exceedingly fortunate. So and my salary is paid by the citizens of Calvert County. And 60% of the museum's funding comes from Calvert County government. So the balance we raise from the concert that we do. And I'm also very fortunate as well, excuse me, to have an endowment for this. And we have a fabulous exhibit department. And some of those past, these 2 gentlemen are no longer there, Stinshire and Shoemaker, great artists that have done some of the art that you saw here. So thank you for your attention. And if you have any questions, I'd be happy to answer that.
Thank you very much, Stephen.